1,000 times more massive than the second and 1,000,000 times more massive than the first, it should raise a big question. How is that possible? Because we should have found 1,000 Borisovs and 1,000,000 Oumuamua before finding one giant icy iceberg of the type that we found. So this should be really a puzzle, and they should have mentioned it as a puzzle, but they don't even mention that. And the second is, why do we have it in the plane of the planets? I mean, obviously, it's a great fortune that all the NASA observatories can look at it, and they mentioned the fact that they look at it. They're really happy about the fact that they could monitor it all the time. But that fact that they can monitor it all the time is really a miracle, because only 1 in 500 incoming objects would be aligned so well with the ecliptic plane of the planets that allows all these NASA assets to be used.
On December 4th, a narrow-band spectrograph pointed at 3I Atlas captured something extraordinary. Amid the chaotic dust plumes and debris trails that had surrounded the object for weeks, a new signal emerged, a signature consistent with ammonia-laced cryovolcanic ice. This wasn't a passive sublimation event, it was a directed ejection, timed with a thermal spike that occurred just 41 minutes after the object rotated into full solar exposure. That alone raised eyebrows. But what truly shocked the scientific community was the depth of the ice layer. Based on the molecular breakdown, this wasn't surface frost or sun-baked ice melting off the crust. This came from beneath, likely kilometers under a pressure-sealed outer shell. The water molecules were unusually pure, suggesting that they'd remained insulated from cosmic radiation since the object left its origin point, possibly another star system. Even more curious, the outgassing occurred in a tight beam, localized to a narrow fissure near the object's equator. That indicates internal pressurization, not surface melting. Cryovolcanic ice only erupts this way under specific conditions: trapped volatiles, structural weakening, and thermal imbalance. And until now, such activity had only been seen on icy moons near gas giants, never on an interstellar object moving at hyperbolic velocity. What this suggests is that 3I Atlas isn't inert, it's pressurized, it's structured, and it's waking up. What triggered the release, solar radiation, rotational stress, or something deeper, remains unknown. But the fact that it's happening as the object closes in toward Earth changes the entire threat profile. This is no longer a passive traveller, it's an active system, releasing ancient ice into space in ways we don't fully understand. And it's just the beginning. Cryovolcanism isn't just a geological footnote, it's a sign of internal complexity. When detected on moons like Enceladus or Europa, it implies a layered structure, thermal gradients, and even potential subsurface oceans. But 3I Atlas isn't orbiting a planet. It's not being flexed by tidal forces. It's not part of any known system, and yet it's erupting. That breaks the pattern. The detection of cryovolcanic ice means that this object holds internal reservoirs of pressure. It's not simply reacting to solar heat, it's regulating its own pressure from within. That implies the existence of structural zones, a crust strong enough to hold volatile compounds, a subsurface layer warm enough to induce phase change, and some kind of internal stress mechanism capable of breaching that crust. This rewrites what we thought interstellar visitors could be. Most comets are loosely bound rubble piles, fragments held together by gravity and cold. They lose material passively as they warm, but what we're seeing with 3I Atlas is directional venting. That requires insulation, pressure, and a trigger. Something, perhaps its retrograde trajectory through varying solar radiation angles, is activating zones one at a time, and that brings up a more urgent issue. If it has one active cryovolcanic vent, it likely has more. And as the object rotates and absorbs more solar heat, additional eruptions may follow. Each event alters its mass, its spin, and potentially its trajectory. That makes it harder to model, harder to track, and much harder to predict. Cryovolcanism means we're not dealing with an inert object. We're watching an evolving one. An evolution in motion always carries risk, especially when the object is on a path toward Earth. Standard cometary outgassing involves water, carbon monoxide, carbon dioxide, and traces of silicates. But the ejector from 3I Atlas contained ammonia, methane, and traces of ethylene glycol, all wrapped in an unusually low-ratio deuterium profile. That profile doesn't match any known comet in the solar system. What does that mean? The DH ratio, deuterium to hydrogen, acts like a fingerprint for the region in which an icy object formed. Most comets from the Oort cloud or Kuiper belt have high deuterium counts, reflecting the cold, dense outer solar nebula. But 3I Atlas has a strikingly low deuterium level, which suggests formation much closer to a star or in a different protostellar disk altogether. That's when astronomers began to widen their analysis. The presence of ethylene glycol, an organic compound rarely found in natural comets, caused further concern. Not because it's exotic, but because of the pattern. It co-occurred with unexpected nitrogen isotopes and trace silicon compounds that only form at moderate temperatures. This implies thermal cycling, a past history of heating and cooling, likely over geological timeframes. Taken together, these markers point to an object that did not form in our system, and perhaps not even in the same way that our solar system's comets did. Instead of being a frozen relic, 3I Atlas might be a processed body, something that underwent heating, differentiation, and resurfacing long before it ever arrived here. And if it didn't form like a comet, it may not behave like one. If this object was ever part of a larger structure or engineered system, then the chemistry isn't a surprise, it's a clue, and that clue points away from nature. After the initial ice ejection, high-resolution images from ESA's La Palma Observatory revealed a startling pattern. The fissures on the surface of 3I Atlas were not random. They appeared in a latitudinal band, precisely aligned with solar incidence angles as the object spun. That might seem coincidental, but it's not. The alignment implies that as the object rotates, specific regions are regularly exposed to thermal energy from the sun, and those regions are exactly where outgassing occurs. This behavior isn't typical. Natural comets do sublimate from the sunward side, yes, but they don't rupture in a pattern. Their surfaces crack chaotically, often collapsing under uneven pressure. 3I Atlas is different. The fissures appear evenly spaced, following angular intervals that map almost perfectly to its spin rate and orbital tilt. That suggests a pre-existing structural tension, as if the surface was designed to fail in response to sunlight at specific intervals. One theory is that the crust is brittle, composed of layered silicate ice composites. Another theory is more disturbing. The object contains embedded stress lines, much like cooling cracks in engineered glass. If true, then these fissures are not just reaction points, they are functional weaknesses. We're now looking at the possibility that 3I Atlas's surface has been engineered or templated in a way that mimics structural harmonics. In other words, it may be responding to the sun not just thermally, but resonantly, venting at the precise moments its shell reaches peak stress under solar torque. This would explain why the cryovolcanic release wasn't random, and why more may be coming. The deeper question becomes, what's beneath these fissures? And was the timing of this eruption part of a much larger sequence? Most comets follow elliptical orbits within the general direction of planetary motion. But 3I Atlas doesn't. It travels retrograde, meaning it moves in the exact opposite direction of the solar system's rotation. That already makes it rare. Less than 2% of known objects do this. But what makes it worse is where that orbit lies, perfectly within the ecliptic plane. Imagine the solar system as a flat plate. Every planet orbits along that plate. Most interstellar objects arrive from steep angles, above or below. 3I Atlas didn't. It came in flat, as if it was aimed directly along the most populated orbital corridor in our system. That's statistically improbable, and dangerous, because travelling retrograde across the ecliptic means every planet it passes is moving toward it, not with it. That increases the relative velocity of any potential interaction, including with Earth. If 3I Atlas were to collide with another object, or experience a gravitational slingshot, the results would be unpredictable. Retrograde velocity translates into higher kinetic energy, more violent fragmentation if a collision occurs, and more chaotic spin states. It also complicates tracking. Models that work for typical comets can't predict 3I Atlas's exact path over long periods. That's because its retrograde motion interacts differently with solar wind, planetary gravity, and the interplanetary magnetic field. Now add cryovolcanic activity to the mix, with pressure bursts shifting its mass in real time. And you get an object that becomes increasingly unstable as it approaches Earth. It's not just on a strange path, it's on a path that magnifies every risk. and no one knows where that path leads if the internal eruptions continue. Over the past 7 days, 3 separate ejections have been recorded from 3I Atlas, each from a different region, each spaced roughly 35 hours apart. What's strange isn't the frequency, it's the consistency. Natural outgassing occurs in erratic pulses, driven by temperature fluctuations or sudden collapses. But this object is shedding mass in nearly identical bursts, with similar durations and comparable material signatures. Each event releases between 7 and 9 million tons of mixed volatiles and crystalline ice. The plume duration, between 24 and 29 minutes. That's too uniform for chaos. It suggests some internal triggering mechanism, possibly thermal thresholds, possibly mechanical release valves beneath the surface. One scenario involves sublimation buildup beneath a rigid shell until pressure fractures the weakest point, but even then, the regular timing remains unexplained. If these are natural cryovolcanic cycles, they're unlike anything ever recorded. Another theory proposes rotational harmonics. As the object spins, internal stress rises cyclically, activating subsurface pockets on a predictable rhythm. That would require an internal geometry capable of storing and releasing energy in pulses. Still another hypothesis is structural modulation. If 3I Atlas was once part of a larger object, or had a controlled formation process, it could contain compartments, chambers, even resonance cavities. The idea of cryogated mass release may sound far-fetched, until you look at the timing. We're watching an object lose mass with discipline, and as that mass exits, it changes spin rate. It changes momentum. It destabilizes the object's internal balance, forcing it into new thermal states. This isn't just about what's leaving the object, it's about what's being revealed underneath. And if those layers are increasingly volatile, this may only be the start.